Welcome to Intro2Astro 2024.
My name is Maria. I am a soon-to-be fourth-year grad student at the Institute for Astronomy, the same place where Faye works. My research is based around adaptive optics, which you will learn more about in one of the upcoming sessions. I do both observational science and instrumentation. My observations are centered around imaging what are called protoplanetary disks and fitting models to them to understand how different structures in those disks are formed. And my instrumentation work involves an upgrade to the existing adaptive optics system at Keck, something which I can probably talk a little bit more about when I'm doing the Intro to AO lecture. So in the next, 7 minutes, I will, in very important astronomy package in Python. Hopefully I can get through most of what I planned. It's called Astropy. It basically contains almost everything you need within the realm of astronomy research, depending on the problem in astronomy that you're dealing with, whether it's to plot a model to a data set, to analyze your data set, to predict something based on predict something based on the data you have so far. Astropy and its associated packages have a lot of different tools, and I will try my best to introduce those tools. So in this lesson, I will quickly go over what Astropy is, what are some of the sub-packages, and some important sub-packages that I think you need to know. And if we have time, I can also answer some of your questions in the end. So what is Astropy? It is a Python package that offers a variety of tools and functions, which, as I mentioned earlier, is useful for astronomy and astrophysics, whether it's to plan an observation, to reduce the data you've got from an observing run, analyzing the data, and or having to do other arithmetic modeling tasks involving the set data. So the one part that I accidentally skipped, but I can probably quickly show you guys is how to install or import Astropy if you don't have it installed already. So you can use pip, which is the standard Python package installer. So it's very simple. It's just pip install Astropy. Or if you're using Conda, you can also use Conda install Astropy. But prior to this session, you might have already installed Anaconda, in which case you don't need to separately install Astropy, because Anaconda comes with a lot of STEM packages like NumPy and SciPy, which you just saw earlier, and even Astropy. But if you want to update it, you can do Conda update Astropy, which will either tell you already have the latest version of Astropy, or if you have an older version, it will update it for you. The last one, I understand it's a bit complicated, but if you want to install Astropy, but you're not exactly sure if you have all the packages that you need to run things in Astropy, like NumPy, SciPy, Matplotlib. Matplotlib is a plotting package. You can sort of run this line. All of this is recorded, and I will be uploading these slides soon, so you'll have the information with you. So speaking about sub packages, you don't import Astropy as it is to your notebook or your script, because Astropy is very heavy of a package. Instead, you will import the sub packages that you need, or the classes within the sub packages, depending on what your script is going to be about, what you're going to be doing in your notebook, so on and so forth. So this is sort of the standard syntax you would use. So if you're importing one sub package, the entirety of the sub package, you can do from Astropy import sub package. Or if the sub package has a really lengthy name and you don't want to repeat that name over and over again, just like you imported NumPy saying import NumPy as NP, you can do import astropy.subpackage as whatever initially you want to give your sub package. Here I just gave it S. Sometimes a sub package has a lot of different classes in it, which can be overwhelming, and you just require one or two classes from that entire sub package. What all of this means will be a little bit more evident when I show you some examples. So if that's the case, you can think of a class as a sub package. A class is sort of like an umbrella that contains different functions that can all be categorized into one purpose. So you can do from astropy.subpackage import class. With Astropy, you not only have subpackages that come with Astropy, there are also what are called coordinated and affiliated packages, which are all packages within the Astropy project community. These packages need to be imported separately in order to utilize their functionalities. The difference is very small. Coordinate packages are those that are maintained by Astropy itself. It's the same people who wrote those packages, and they used in association with the Astropy library. Affiliated packages are other packages that are used for astronomy, but because they're widely used and because they rely on libraries written within Astropy, they are often seen as associated with Astropy. So some examples of subpackages, and I hope to go at least through two of these, are units, which help you convert or handle different kinds of units in astronomy, because astronomers are notorious for not sticking to one set of units. We don't always use SI units for things because it is impossible to code distances between stars and planets in meters. We sometimes use astronomical units. Then if you have to describe distances from Earth, we would go to parsecs and light years. So to convert between units when you're doing arithmetic calculations, we have a unit subpackage, and to avoid having to rewrite different constants and store them as variables over and over again, we have a subpackage for that called constants. If we want an easy way to find coordinates and define coordinates for different things that we're observing or the location from where we're observing, we have the coordinate subpackage. These are just a few examples. Astropy has a lot more. Some examples of coordinated packages. There's one called AstroQuery where we can use it to look up a target of your choice and get all the information you need. Instead of you having to go through different libraries, you can use AstroQuery and it goes through all those libraries for you, like Simbad, Vizier, etc. CCD-proc is to do basic CCD data reduction. CCD is a type of detector, and images taken with those sorts of detectors have to go through a certain procedure before you can actually look at the things you've taken using those things that you've imaged using those detectors. So CCD-proc is a standard data reduction library. PhotoUtils is used for photometry when you have to measure the brightness of an object you imaged the brightness of a star or brightness of something that looks like a star. And it also has other image processing tools. And these are maintained by Astropy. And when you import and use these packages, you also have to import Astropy. Or you probably don't have to. I always do because I used both together. Affiliated packages, as I mentioned earlier, they're written by other people, but they are seen as a part of the Astropy family because they're used by the astronomy community. One that has been super helpful for me is AstroPlan, which you use to plan observations. Then there's AstroML. Machine learning and data mining is extremely important nowadays in astronomy when you're parsing through a lot of data and a lot of archival data, those that are captured by telescopes on ground and space. So AstroML is very handy in that respect. For those interested in studying interstellar medium and the dust in the interstellar medium, dust extinction is a useful package as well. Okay, so now that since I see that we're already past the hour, I have time to go over one set of packages for using astronomical quantities. So we have two of those, astropy.units and astropy.constants. As I mentioned earlier, astropy.units is helpful when you're handling and calculating using different quantities with different units. So this is how you'd import it. You can either do from Astropy import units or import astropy.units. I like to give it an initial. Most people do, because if you're using different units like meter or centimeter, you don't want to keep writing units.meter, units.centimeter, units.parsec. It becomes clunky. So we use a shorthand U or whatever letter you like. So for example, I want to define a velocity quantity. And this is how you would do it. You would take your number, you would take your value, and then you would multiply it by whatever unit you need. So I want to define my velocity meters per second. So I take 15 times u dot meter divided by 32 times u dot second. And if I print the value, and if I print simply Q, I get the whole thing. If I print simply the value, I get what the value is. If I print the unit, I get whatever unit I defined it. And these units are stored within the variable. So in case I have to, let's say, multiply this velocity with a distance that is defined in parsecs, all I have to do is define a distance variable, like d is equal to 30, let's say 30 parsec. So 30 times u dot pc or u dot parsec. And then if I do whatever calculation I need to do with it, Astropy would see them as a velocity object in one set of units and a distance object in another set of units, and does the calculation. And within that, it will know how to convert between the units and give the answer, typically in SI units, or if you want the answer in a specific set of units, you can do that as well. And that is by using the function dot to. So let's say I have a distance that is in parsec, 1 parsec, and I want to display this distance in kilometer. All I have to do is the variable dot to, and within the parentheses, I would give it the keyword argument u dot km. So it knows to convert 1 parsec to the equivalent number of kilometers, and that would give me the value 3 times 10 to the 13 kilometers, which is what 1 parsec is. And then the other quantities related package is astropy.constants. So I can import it the same way I imported units. And what this does is it comes loaded with almost pretty much the most used constants in astronomy, the universal gravitational constant, the Stefan-Boltzmann constant. If you don't know what this is, it's a constant that we use when we're calculating fluxes and luminosities. Basically, a lot of constants that you use in astronomical problems, instead of having to rewrite them yourself and define units for them and store them as variables. Sometimes it's very handy to just have a library of these so you don't have to define them on your own. So this is tied with so you can import this, and let's say if I want to print one constant, I want to print the universal gravitational constant. So I do print c.g, it'll give me all the details. It'll give me the value. Well, whoops, sorry about that. It'll give me what the value is. It'll give me what the uncertainty is, what its default units are, everything. So I had a problem set for you. I was going to show you the answer, but since I'm out of time, I wouldn't. And the notebook for all of this will be uploaded very soon, and I will send a message on Discord once that's done. So a little assignment I had for you guys was to calculate the gravitational force between a star and a planet which are a certain distance apart. The equation is very simple. If you don't know it already, you can look it up. And the goal is to use astropy.units and astropy.constants to do this calculation. So in astronomy, if this convention is confusing to you, in astronomy, we often have like objects at varying sizes, both speaking linearly or radially, as well as in terms of its mass. So it becomes very difficult to keep mentioning things in kilograms or kilometers. So we use shorthands like a solar mass. So a solar mass is the mass of the sun, or Jupiter mass, which is mass of Jupiter. So we often define mass of planets as Jupiter mass or Earth mass, and mass of stars as a solar mass, or how many solar masses they are. And astropy.units does have those as actual units. So you can literally just look up what the shorthand is for solar mass and what the shorthand is for Jupiter mass, and you will get what the relevant units are, and you can use that to solve your problem. AU is astronomical unit. AU is the distance. 1 AU is the distance between the Earth and the Sun, and AU is often used when we are talking about distances between a star and its neighboring companion. So this is a problem that you can try out. I will lay out the context for you and a lot more information to help you with this in the notebook that I'll be uploading tonight. Let's see.
All right, thank you, Maria.
Yes, and I think I just had one more thing to show you guys in the end. Let's see. Yeah, these were some few websites that I noticed. If you look up, because Astropy is very dense, it has a lot more information. And originally I timed this presentation for 20 minutes, so obviously I can't cover everything. But there are a lot of modules, documentation released by Astropy itself, and lessons written for astronomy programs that delve into how to use Astropy, how to use its different functionalities for everything that you require. So I would highly recommend going through these lessons, doing the practice problems they have, and that will really help you becoming efficient in this. And no one learns Astropy at one go. Most of us still use the documentation from time to time to be able to use these functions. So yeah, feel free to ask any questions you have and to keep going back to these documentations for whatever you need. And this is not just true for Astropy, it's true for literally every Python package that we're introducing to you through this module.
Register now on bit.ly/Intro2Astro 2024.